Значит, да, Саш, ну тогда я думаю, что твоя идея, может, и подходит.
А вот Зирань подсоединился, все.
Uh,
Да, так что все-таки лучше по-английски.
okay, okay.
Okay, so I think it's high time to start. So our first, I'm happy to greet everyone at our first seminar this semester. And our first speaker will be Professor Andrey Smilga from Nantes University. And okay, I think that it would be better to read the title of his talk from the screen rather than from the announcement I made. Benign ghosts, mechanical and field theory systems. And I also hope, and I think it will, be related to KdV equations, but we will see. Okay.
Yes, the KdV equation, it will come. So first I want, can I start already, right?
Yes.
So I just asked to excuse me because I'm not a mathematician, and even though the subject which I'm going to talk about is very simple, and I think it will be understood to everybody, but the languages, physics and mathematical languages are different. And so I know that it's difficult for me to understand, for example, some mathematical talk or mathematical paper, when even if it's on the subject which I more or less know, and maybe it's reciprocal. So please ask as much questions as possible, and it will be better, not only, I think it will be better for everybody. So what are ghosts? I will explain what are ghosts. But first, let me start with the motivation of these studies, why I started all that. I am interested in higher derivative theories with more than 2 derivatives in the Lagrangian. And let me explain why. There is some motivation which indeed has something to do with quantum field theory, and everything else in my talk will have little relationship to quantum field theory. So the motivation is the following. We don't know what is the fundamental theory which unifies all interaction and governs our world. It's so-called Tower theory of everything. So what is it? There was a dream by Einstein who tried to unite electromagnetic and gravitational interactions. This dream didn't realize at that time, and even now we cannot boast of much of progress in this direction. There is so-called standard model, which indeed unifies so-called strong, weak, and electromagnetic interactions, but gravity is still a mystery. We don't know what is quantum theory of gravity. Even classical theory of gravity, general relativity, is not consistent because, well, there are black holes and horizons, event horizons, which actually lead to violation of causality, and so at some point. And now, what is this unified theory? And many people think that it's kind of string theory, but I personally, I have a different, I couldn't say opinion, but I guess the reasons are the following. String theory has some conceptual difficulties. What is string theory? So, you know what is usual mechanics, right? Usual mechanics has a finite number of degrees of freedom. You can treat it classically or quantum mechanically, but there is some finite number of degrees of freedom. For example, hydrogen atom, if it's quantum mechanics. And field theory, the dynamical variables of field theory are just functions of coordinate, spatial coordinate, and time. These functions are called fields. It's more complicated, but still it's can be understood if you understand well what is usual mechanics and quantum mechanics. But in string theory, on a really deep fundamental level, the fundamental variables are not just some finite number of numbers. It's not they are not functions, they are functionals, which depend on string configuration, right? This phi of C. The theory of these functionals is not developed. It's what, well, theorists call third quantization or string field theory, and we still don't know what is it. There are some progress in field theory, but at more superficial level. If you want, string theory is like a beautiful building, but you can watch it only starting from, let's say, second floor. And what is on the first floor, on the ground floor, and what are the basements, I just don't know, are not known. Okay, so the only alternative is that the theory of everything is field theory. But then it should be formulated not in our four-dimensional space-time, but in some high-dimensional space-time, because, well, we know there is gravity, so our four-dimensional space-time is curved, that we know. And in the framework of field theory, it can be only explained if you think that our universe is embedded in some bulk space, what is called, of high dimension. So if you think seriously that fundamental theory of everything is a field theory in high dimension, then you meet problems, right? And the most serious problem is renormalizability. So what is it? If you, for example, take 6 dimension and you try to write something like electrodynamics, I may ask, do you know just usual action of usual photodynamics? It's F mu squared, from which Maxwell equation follow. It's not trivial equation. Not all mathematicians know that. So this F mu is familiar for you or not?
Well, I believe it is. It looks like, actually, it resembles me the Young-Mills action, but I believe it's not.
Yes, Young-Mills action is like that, but just electrodynamics is simpler. I don't write here the color index, right? It's not a method, but just a tensor.
I thought it was 3-dimensional, but you say it's 6-dimensional, so that's a little bit confusing.
Well, okay, exactly. So usual Maxwell theory is in 4 dimensions. We live in 4 dimensions, right?
Yeah.
But try to write something like that, but in 6 dimensions.
Oh, I see.
It's just a try. And if you write it, then the action is dimensionless. And to make it dimensionless, you should write before the integral some dimension full constant, which has the dimension of mass squared. And if you do that, then you meet problem, because theory is not renormalizable, which means that it's plugged by ultraviolet divergences. So there are some loops, well, in some higher orders of perturbation theory, and in 4 dimensions they're tractable for such a theory, and in 6 dimensions they're not tractable, they diverge badly. And that means that you just cannot, you don't know what is it, you cannot define this field theory. Usual 4-dimensional renormalizable field theories can be defined. For example, you can discretize it. And well, the problem is usually with so-called path integral, but I will not well pursue this discussion. But this path integral can be discretized and represented as just a limit of some finite dimensional integral. And if you do the same in 6 dimensions, then you just see that this limit doesn't exist, it diverges. And so usual field theories with 2 derivatives are not defined in if number of dimensions is larger than 4. Okay, what you can try is to write a higher derivative theory. So you can, for example, if you're in 6 dimensions, you can add 2 derivatives. And then the coupling constant will be dimensionless. And such a theory, well, this is a free theory which I have written, but you can write more complicated theories with higher derivatives and with dimensionless coupling. And then they're normalizable in the sense that ultraviolet divergences can be treated there. But these theories have another problem. And this problem is that they involve ghosts. If a theory has higher time derivatives, then there is no vacuum state. The Hamiltonian just doesn't have ground state as we are used to have it in usual field theories and hydrogen atom also. Usual quantum systems, they also have a ground state, the state with the minimal energy. And if you have higher derivatives, higher time derivatives in the Lagrangian, this property is lost. So my talk will be exactly about the theories with high time derivatives. And I will try to convince you that not all such theories are bad. Sometimes they don't have internal contradictions and can be treated and studied. That's the main message of my talk. And KdV just rotated when you follow not time evolution of KdV, but it's spatial evolution. You have high derivatives in space, but if you call space time, then it's high derivatives in time. And if you study spatial evolution of ordinary KdV, so you are actually studying high derivative theory. Now, what are these ghosts? By definition, so well, it's however it's spoken on mathematical seminar, and I have to give some definitions. So I will give only one definition, actually. Everything else will be more heuristic, if you want.
Okay.
So ghost system is a system where the spectrum of quantum Hamiltonian doesn't have a ground state. Now, why it's called ghost? It's called ghost by historical reasons. People didn't like quantum systems without a ground state, and they tried to force the system to have a ground state. It's possible to do, but then the metric of the Hilbert space is not positive definite anymore. There is no, how to say, conservation of probability, that means. And there are some states which in other formulation are just the states with very much negative energies. And in the language which was common until very recent days, people talk about ghosts, the state with negative norm. That's there is no other word, and so I call them also ghosts.
Because nowadays it's almost kind of universal accepted lingo to say ghost about certain, well, fields which you add artificially to make your construction look more homologically plausible. Okay.
Okay, so there are so-called Fadeev-Popov ghosts in Young-Mills theory.
Yeah, that's more or less what I meant.
And they are also, well, they also have negative, negative norm. But as the states don't exist as the states of the Hamiltonian, that doesn't spoil basic properties of the theory, like unitarity, for example. Because these ghosts, they appear only in the loops. And actually, there is also a way, well, not to introduce the ghosts. That depends on some particular gauge which you choose, but it's completely different stories. So Fadeev-Popov ghosts are not physical ghosts in the sense that they don't exist in physical space. It's just some device to calculate the Feynman graphs, okay? And here I will talk about real physical ghosts, states, systems with no ground state. And so this situation is inherent in any theory where the Lagrangian has more than 2 time derivatives. I will not explain it well mathematically, will not prove theorem, but I will give you an example and you will understand where it comes from. Actually, there are 2 theorems. The theorems a little bit later. And now, just how to describe a system with high derivatives in the Lagrangian. Ostrogradsky, well, a very long time ago, in 1850, just developed a general technique for that. Actually, that was a paper published in French in the memoirs of Petersburg, Presidium of Petersburg Academy of Science. And there he developed Hamiltonian formalism, actually. And he did it independently of Hamilton. And why? Because the paper of Hamilton was several years earlier, but that was in English. And at that time, English was not a generically accepted language of science. Latin already was not such a language, and English not yet. And so Ostrogradsky, he knew well French because he was a postdoc in Paris. His most known paper is about Ostrogradsky theorem and vector analysis. You know that, right? And he did it somewhere in 20s when he was a postdoc in Paris. And so he did it independently. And also he considered the high derivative theory. And so, well, these Hamiltonians corresponding to high derivative theories are called Ostrogradsky Hamiltonians. Ostrogradsky himself, he didn't study dynamical aspects of these theories. He only shown a way to write Hamiltonians, but he didn't study the dynamics. But 100 years later, in 1950, a paper appeared which shown that such systems will involve these ghosts. And that was done by Pais and Uhlenbeck, well, in 1950.
So is this Uhlenbeck, is this the father of Karen Uhlenbeck?
I don't know. Probably it's namesake. I don't know actually. It's another person that I know, but
yeah,
whether he is a relative or not, I don't know.
Because this Karen Uhlenbeck, she's pretty famous. She got
Yes, it's not the famous Uhlenbeck. It's another Uhlenbeck, but
that famous. She's a woman actually. So this.
Okay, I didn't know that. Sorry, but this paper is also good, very good paper.
Okay, I see.
Now about theorems.
Wait, Gosha, are you sure that it's the same Uhlenbeck? Because Ullenberg was
No,
called
that's different.
Karin.
Yes,
And here is
precisely,
she.
I meant, but that's probably her father.
Yeah, I think so.
That's what I say.
Maybe, well, this Karin Ullenberg, how old is she? Well, that's the paper of 1950. That means that the author was born at least 100 years ago, right?
Yeah, she's from 1940s, I believe. She's from 1940s.
Born in 1940s, right?
Yes,
Yeah,
yes. I think it's her father, not she itself.
Yes, yes. I heard that your father was also a mathematician. That's
possible, but that's a paper not exactly on mathematics. It's a paper on quantum field theory. So it's written the way which I can understand. So here, this Ullenberg was probably not a mathematician, because otherwise
maybe
the paper would be written differently.
Maybe. Well, just
So there are two theorems which one can prove. One is actually very simple. As soon as you write this Ostrogradsky Hamiltonian, you immediately observe, for higher derivative theory, you immediately observe that it's not positive definite. It can be positive and negative. I will give an example a little bit later. Even this Woodard, to the best of my knowledge, he was the first person who just formulated it as a general statement, but it's so simple statement that he attributed the statement to Ostrogradsky, which, well, not correct. And now the same about quantum mechanics. So one can prove that quantum counterpart of this high derivative theory has this, as I told you, the spectrum is not bounded from below, and it's also not bounded from above. Okay, now an example of a ghost system. So that's two oscillators, right? One moment, there is a printer works. I just want, again, that's you are doing that. So just take two oscillators, but the second oscillator with a negative sign, right? That's all.
Yeah.
Very simple system. And of course, that's the spectrum. And it has positive as large as you want, positive, and as negative as you want, also energies. Now, all the states are normalizable. Well, there is, mathematicians call it pure point spectrum. Now, if the ratio is rational of two frequencies, then there is infinite degeneracy of all the levels. And if this ratio is irrational, then it's everywhere dense, the spectrum. So, of course, it's unusual, but there is nothing wrong about that. It's a very simple system, but you can consider it.
It seems that the system doesn't involve high derivatives. Yeah, it's just the easiest.
Well, high derivatives will come. Just,
but not right now. Okay.
Right now, not. It's just the simplest system which one can imagine, where there are ghosts, right? High derivatives will come on the next slide. And that's the system which is called Piaget-Ullenberg oscillator, right? And you see here high derivatives in the Lagrangian. And if you build up a Hamiltonian, which corresponds to this Lagrangian, how do you build it up? You just require that Hamilton equations of motion, well, would be equivalent to Lagrangian equations of motion, that's all. And you see here two pairs of variables, right? X and the momentum corresponding to X, and the velocity V, X dot, that is, and the momentum corresponding to this velocity. And you see the linear term. px times v. And that's why the Hamiltonian is not positive definite. It can be positive, well, very large and very large, well, negative, but with large absolute value. And if the frequencies are not the same, you can make a canonical transformation. You see, it's also a quadratic system, right? So, well, it's quadratic. There exists a canonical transformation which will gives you exactly this Hamiltonian. There is large p, large x, which are some functions of the variables here, and you can bring this this Hamiltonian to the Hamiltonian which I've written. So that's how derivatives appear, right? Now that's free system, and there is nothing wrong in this system. But if you include interactions, then you might have a serious problem. There is a danger of blow up or collapse. In classical mechanics, that means that just equations of motion, following the equations of motion, you reach singularity at finite time. That's blow up. And the corresponding quantum system is not unitary. Unitarity is violated. For example, if you just include nonlinear interaction like that, just add the term x to the fourth power. That's exactly what happens. Heuristically, so there are some degrees of freedom with positive energies and with negative energies. And when start to interact, then the negative energy can become very, very low, and the positive energy can become very, very large, such that the sum of them is still conserved. And that's the reason of this collapse. So these systems are not benign. Now, what is the simplest problem where this happens, where the blow up happens? The simplest problem which I know is the problem of attractive potential 1 over r squared. That's so-called falling to the center phenomenon. Consider this Hamiltonian, not high derivative Hamiltonian. This is not high derivative, but it has very strong attractive potential. Consider classical trajectories of this Hamiltonian. And then if the energy is positive, then they escape to infinity. And if the energy is negative, so it's slightly negative, then it goes by a spiral and it hits zero, singularity of the potential, right, at finite time. So that's what happens in classical theory. And in quantum theory, situation is a little bit better, because quantum fluctuations, they kind of resist this tendency to go to the center. And if this coefficient kappa is not too large, then the quantum problem is quite benign. Hamiltonian has ground state. But if this parameter kappa is larger than some limit, well, this is the limit, then your lost quantum spectrum is not bounded from below, and which is worse, unitarity is lost. If you want, again, heuristically, the probability leaks into the singularity. So
can you show me the equation again?
There's the Hamiltonian, yes.
Yeah, Hamiltonian, just
three-dimensional.
Is it true that everything is still happens on a plane? I mean, in Newton.
No. That's three-dimensional Hamiltonian.
I mean, in classical mechanics, when you work with Newton's gravitation force, it's easy to show that the system is actually planar, right? When
well,
potential
okay.
is no power.
Well, okay. So classically, yes, but I'm not sure about quantum mechanics now. So I'm a little bit confused now. So, you know, colon interaction is 1 over r, right? In 3 dimensions. And
yes,
that's the attractive potential 1 over r squared, more singular. And I never looked, never studied what happens with the quantum Hamiltonian like that on the plane.
I see.
But in 3 dimensions, I know what happens if kappa is larger than 1/8 in mass, inverse mass units, then unitarity is lost. So there is a corresponding paragraph in quantum mechanics of Landau-Lifshitz. So it's very well known phenomenon. Now you can regularize it, regularize singularity. For example, you can require that the potential is 1 over r squared for the radius larger than something, and then it's a constant. Then you can, of course, solve Schrödinger equation, no problem, but the spectrum of the Hamiltonian will have ground state, but all the levels will depend on this regularization parameter A. So that's what happens. Now, in this case, one can say that there are ghosts, and the ghosts are malignant, right? It's like tumor. Tumor may be benign, may be malignant, right? And in this case, the ghosts are malignant. Now, it happens that there are many systems where the ghosts are there in this definition which I given before, but which are benign, where there is no blow up in classical theory, and there is no loss of unitarity in quantum theory. In this, on this point, at this point, one can make an observation, because of course the main interest for me, for all physicists, is quantum theory, right? But it's more complicated to study quantum dynamics. Classical dynamics is simpler. And so, just an observation, I don't know how to prove the theorem, but it works in all cases, and the reason is also clear. If classical quantum theory is sick, then also classical counterpart is sick. And on the other hand, if classical theory is benign, for example, there are no trajectories which run into singularity, then a quantum version is also benign. Why is that? Because, as I said, quantum fluctuations always make the singularity more smooth. They kind of, cope with the effects of singularity. And so in this example also, that was clear. If kappa is 1/10, for example, then classically there is blow up for some trajectories, but Hamiltonian is okay. And that's why to study whether quantum theory is benign or malignant, it's not necessary to study quantum dynamics. It's enough to study classical dynamics. And that's why...
I mean, just didn't quite understand. You said that if classical is malignant, then so is the quantum.
No, it's not exactly like that. If classical is benign, then the quantum theory is also benign.
Okay.
And the inverse of that is written the first sentence, right? But it's possible that classical theory is malignant in the sense that there are trajectories which go to singularity, but still quantum Hamiltonian exists and has a down state.
Okay, I see. Thanks.
Okay, so there are, however, I started with free system, right? Peisel and Becker's oscillator was a free system, and the first example was very simple, just two oscillators, positive and negative. It was a free system. And I said that if you include interaction, then you meet problem. You may meet and may also not meet. That's my main point. So there are some non-trivial, non-linear systems which involve higher derivatives and where ghosts are benign. And probably the first example of such theory was constructed by Didier Robert. Didier Robert is a mathematician. He is an expert in functional analysis. He is already retired, but he worked in MAN. And so, our starting point was some supersymmetric theory, but it's not important. I will not.
Can you please repeat what a benign ghost?
Benign ghost is the system where there are no ground state in the Hamiltonian, but still there is no loss of unitarity.
I see. So one can actually get infinitely negative negative eigenvalues of arbitrary size.
Yes, but the evolution operator, you can write the evolution operator and it's unitary.
Okay, I see.
That's at the quantum level. At the classical level, there are no blow-up trajectories.
Okay.
And there is relationship, but I showed what is the relationship. So this system is very simple, as you see, very simple Hamiltonian. So there are two pairs of degrees of freedom, small p, small x, and canonical momentum p, and small d, and canonical momentum large p, right? That's the Hamiltonian. And you see that it's not positive definite. Well, classically, it has ghosts. And now, this Hamiltonian is exactly solvable because there are two integrals of motion, the Hamiltonian himself, and that's the second integral of motion. And so, well, you can just write the solutions of the classical and of the quantum problem analytically. Actually, well, I saw the book by Askol Perelomov devoted to integrable systems, and he lists, there is some lists of integrable systems with 2 degrees of freedom, right? And this Hamiltonian is not there because he just didn't consider such crazy Hamiltonian, which is not positive definite. But it is exactly solvable. An example, take the potential here, quartic potential, right? Now, the solutions then of the classical equations of motion can be expressed via elliptic function. This x is just elliptic cosine because it's like a motion in the quartic potential. You see, it's just the motion. It is, you can consider the spectrum of n, not of Hamiltonian, but of n. And it's just a motion. I'm not talking about spectrum. You can consider the classical dynamics of associated with this n. So this x is elliptic cosine, and d involves some linear, well, it's proportional to time. The amplitude rises with time. So it looks like that. So some irregular behavior, but the amplitude grows with time. But it's not blow up. So that's what I've written here. D as a function of time behaves like that, and x is just bounded. And there are now many other benign ghost systems are known. Here are just 3 sample references. Now, not only classical problem for this Hamiltonian, but also quantum problem is exactly soluble. That is, you can find the spectrum and express the eigenfunctions of the Hamiltonian in quadratures as an integral. And that's the spectrum. It looks unusual, but there is nothing wrong. There is no internal contradictions. There are many states, it's infinite degeneracy with 0 energy. Then there are bands of continuous spectrum. So they start from omega. Omega is just the parameter in the potential, right? Here, right? With 2 omega, 3 omega, and the same on the negative side. So there are states of continuum spectrum with positive energies and with negative energies, and also a lot of states with 0 energy. Now we will go to integrable models. So some of these systems, ghost systems, are not integrable. Integrability is not necessary, but it helps. If you have an integrable system, then, well, first of all, it's easy. You can treat it easily. And also, well, many such systems are with not positive definite Hamiltonian, have ghosts which are benign. And the simplest probably example is the Toda chain. Well, Toda chain, that's the Hamiltonian, right? This Hamiltonian is positive definite. You know, of course, in this seminar, I think you know well this Toda chain better than I. And it has other integrals of motion. So that's exactly soluble. Here you have 3 degrees of freedom. There is an obvious integral of motion, which is the sum of 3 momenta. But there is also cubic integral of motion, I. Now, the idea is very simple. Main idea is very simple. You can consider not the spectrum of the Hamiltonian, but the spectrum of I, of the quantum operator, which corresponds to I. It's cubic in momenta, and so it is not positive definite. And so if you just call this I Hamiltonian, then this Hamiltonian involves ghosts. But the trajectories are still, well, simple. Well, there is no chaos. It's exactly soluble system. Now the spectrum quantum is discrete, and as far as classical trajectories are concerned, you can solve equations of motion numerically, for example. And that's what you obtain. They're a little bit different. So you can write Hamilton equations of motion, which correspond to original Hamiltonian H. And that's what you obtain. That's that's how one of the momenta, P1, depends on time, right? And you see some regular behavior. And that's how the same P1 depends on time if the equations of motion which you write don't correspond to H, but to I. You can very well write Hamilton equations of motion for I. And then it's also regular motion, but you see some, well, beats, you see some beats here. Here also you see beats because, well, I stopped it here, and then it goes down and starts, but the period of the beats is large, and here it's small. So that's just technicalities, well, some particular initial conditions. And now more recent work, which I did together with Thibaut Damour. Thibaut Damour is a physicist. He is an expert in normal and general relativity, other gravity theories. He works in ISHES. Now he is retired. And so when I came to ISHES as a visitor, we just wrote this paper together. So we found many other, just noticed the existence of many other benign ghost systems. One class of such systems, well, can be derived from some ordinary system. And an example how this Hamiltonian of Robert and myself can be derived by this more general method. So you start with the usual benign quadratic Lagrangian. Then you just write, instead of x plus epsilon d. Then you treat d as a new variable. And you expand what you obtain in epsilon and keep only the linear term. So here it's not higher derivative, it's just a Lagrangian. You will obtain a Lagrangian, which corresponds to the Hamiltonian p times, well, again, I will show it to you. Unfortunately, you see it would be much better with large blackboard, then some formulas would be left, right? One could just show them, but well, so there's
so we have blackboard. Unfortunately, we're not in position to to choose now. Unfortunately, we're not in a position to choose now. I mean,
yes, of course. So that's the Hamiltonian is not higher derivative, and Lagrangian is also not higher derivative, which corresponds to that, but it can be generated from just usual quadratic Lagrangian. That's the point. Again, right? You start from this L0, you trade x for x plus epsilon d, then you expand on epsilon, then you obtain some Lagrangian, which depends already on x dot, d, and d dot. And canonical Hamiltonian, well, that was several pages up, right? That's the Lagrangian, right? You obtain this Lagrangian with two pairs of dynamic variables. And that can be done for any usual quadratic system. Well, that's just, well, I repeat something which I already said. So that can be done for any usual Lagrangian with many degrees of freedom, no problem. So you take any Lagrangian, then you trade q by q plus epsilon large q, expand in epsilon, keep the linear term, and then you obtain Lagrangian which has benign ghosts. Also, you can do it for field theories. For example, take Young-Mills Lagrangian, which you know, right? That's Young-Mills Lagrangian. That's in 4 dimensions, right? Not in 6 dimensions, but in 4 dimensions. Now, F mu is, well, made of vector potential, A mu. So, on mathematical language, you know, A is connection, five bundle, and F mu is the curvature form, right? So you just write A plus epsilon b instead of A, expand on epsilon, you obtain some field theory which involves benign ghosts. That's one class of benign ghost systems. Another class are just the motion on Lorentzian manifolds. So usual manifolds have positive definite metric, right? But you can consider the manifold where the metric is not positive definite. That's the example anti-de Sitter. That's the metric. That's the metric of constant curvature. Here it's positive. There is also the system with negative curvature. Now the equations of the geodesics are written here, just motion on this manifold. And they can be even solved. And you obtain some functions which don't exhibit a blow up. The corresponding Hamiltonian, which corresponds to this motion, is not positive definite. Metric is not positive definite. And the Hamiltonian is not positive definite. So it's the system with benign ghosts. As what is written here, that for negative energies, the X can grow exponentially with time, but still it needs infinite time to go to infinity. And so it's not blow up.
Mm-hmm.
And that's the simplest example, but there are many other Lorentzian manifolds with negative metrics which have the same property. Their trajectories correspond, there is no blow up, and the corresponding Hamiltonians involve benign ghosts. And now KdV, something which you were waiting for, right? KdV is also, well, exactly soluble system, right?
Yeah.
Now,
Yes, I just said yes.
yes.
Simple question, I just.
Now, there is an ordinary KdV and modified KdV. And it happens that more ordinary KdV. So what I want to do, I want to, as I already mentioned, and it's in the abstract of the talk, I want to change coordinate on time, places, can change places, right? So if you replace x by time, then you obtain this equation, and it involves high time derivatives. And it follows from the Lagrangian, which also has high derivatives. Here it's second time derivatives, right? So, well, okay, so it's a high derivative system. Now you can do the same, of course, for ordinary KdV, but it happens that for ordinary KdV, you have blow-up trajectories. And for modified KdV, you don't.
Mm-hmm.
So well, I said that I changed the place of x and time, but later it's just more convenient. For me, it was more convenient for us, for Damur and myself, to just write ordinary KdV and modify KdV equation and consider it spatial dynamics, not temporal dynamics, but spatial dynamics. That's what is written here. So temporal dynamics of this equation or spatial dynamics of this equation. And so there are many arguments, but no proof that the classical dynamics of modified KdV is benign. There is no blow up. So let me present these arguments. And that's the second part of my talk. So let's start with ordinary KdV. So why it's not benign? Suppose you look just for classical, for constant solutions, which don't depend on time. Then this equation can be written as like that, or this combination is a constant. But this is just an equation of motion. You just think of x as of time, And that's just equation of motion in cubic potential. And cubic potential, well, it's positive on one side, but it's badly negative on the other side. And so there are blow-up solutions. Actually, you can observe that any such solution, any such function is a solution to this equation. What to this equation?
Yeah, to this equation with no right hand side.
Very well, to this also, because this u doesn't depend on time, right? And so, for example, you solve Cauchy problem, you start with some x, so what should you do? At some point x equals to 0, you should specify the function, the first derivative with respect to x and the second derivative with respect to x, because it's the equation has third x derivatives. And so at x equals to 0, well, you have something, some constant, but then it evolves and it runs into singularity. Now consider modified KdV. So you do the same, for example, and you see that there is no singularity. Again, look for constant solutions. So ut is 0. Now the equation acquires this form, or this function is a constant. And it's also motion.
So where is the kappa in the system of equations? In the second line.
I forgotten to put it there. So here kappa is equal to 1. Kappa is equal to 1 here. Thank you. So you should just multiply it by kappa, right? And here also for kappa. But then it's the motion, it's a motion in quartic potential. Quartic potential, so sorry, indeed, it's not good. Here I write kappa, here I write kappa, and here I don't. So for that. And if kappa is positive, then the potential is, describes the bounded motion. No problem. So I think there is no double S in this word, but you understand. You distinguish for modified KdV a focusing case and defocusing case. And so it's benign in the focusing case and not benign in the defocusing case. If kappa is negative, then it's not benign. And that matches the well-known fact, well, it should be well-known for you, and I just learned it when I started all that. I was not an expert in KdV. There is so-called Miura transformation, which relates any solution of modified KdV equation with negative kappa to the ordinary KdV equation. Ordinary KdV is not benign, and so defocusing modified KdV is also not benign. But it's just one answer, right? What happens more generically. So I don't know what happens generically. As I say, we are not able to prove any theorem. But what we looked at are two things. Another kind of solutions, the scaling solutions. And then we also studied the dynamics numerically. First, scaling solutions. This modified KdV equation has this invariance. So you just multiply the independent variables by some constants. You multiply the variable u by some other constant. And if they are related in this way, so there is actually only one constant, then this equation will preserve its form. And this invariance will allows one to write scaling solutions. Scaling solutions, they have this following form. So alpha is just a real constant. Then, well, that's the time dependence, and then some function which depends on some combination of x and time, right, written here. And then for these answers, you can reduce partial derivative equation to ordinary derivative equation. And this ordinary derivative equation has this form. And that's belong to Pain-Levé, well, class, well, Pain-Levé 2. Again, I am not an expert here, but if you look in Wikipedia or some books, then you find that it is indeed Pain-Levé 2 equation. And this equation, well, the solution was studied, and there are no singularities for positive coupling. There are no singularities here for positive coupling. And so there are no singularities for this particular ansatz for the modified KdV. Now that was two classes of some partial particular solutions. And now about numerical simulations. That's the only thing which we could do more. So we take this modified KdV and define it in the band when t well runs from some interval from 0 to 2 pi, for example, and pose some initial conditions. We try different initial conditions. That's some particular initial conditions which are natural. And then so you should specify the function and x equals 0, the first x derivative at, again, x equals 0, and second x derivative at x equals 0. And so you put the system on computer. And that's what you obtain after some, not time, but so it's again, you see earlier it was just a sign, right? And here what you obtain when some space has passed for some x is equal, in this case, 2.9, right? You obtain some profile, which is no longer sign, but of course it keeps its periodicity, right? But it's not sign, and it doesn't show up any blow up. Unfortunately, if you look, that's the function, right? And it looks smooth. But if you look at the first derivative of this function, then you see some wiggles. And that's high frequency noise, which is a serious problem in numerical calculation. I will explain the origin of this noise a little bit later, okay? And just I show that there is some high frequency noise which doesn't allow you to go too far in X. Then it just increases and you just lose any profile, anything. What one can do is to do the following. So that was just initial condition, it was a sign, right? But you can try to look for another condition. So you see it's elliptic cosine. Why? Because it's just exact solution of modified KdV equation. So you know that such solutions exist when you think in time evolution, but you also can think next evolution. It also exists. That's just an exact solution. But what you can do, so I just defined everything here. It's periodic not only in time. Here, well, the period in time was 2 pi, and it's also periodic in x. Now, no, that was not from 2 pi. The period in time was a little bit less than 2 pi, so it's written here. Now, that's what you obtain after some time. So at x equals to 0, that was some elliptic cosine, some smooth function. And after some x which passed, you also see some function, but already you see this high frequency noise. And if you go further, then you lose the control of anything. Now, what is the origin of this noise? It can be, well, easily understood. Why there is no high frequency noise in ordinary time evolution of ordinary KDV, modified or not modified? Suppose you pose ordinary Cauchy problem at 0 time equals to 0, and then it's some function of x. Then you can, develop it in Fourier integral, present it as a Fourier integral. And what happens with this function after evolution? So, the KdV equation is nonlinear, but you can write, you can look at what happens in linearized KdV, because it's linearized equation which governs all stability or instability. To study the question of stability, it's sufficient to study linearized equations. So it's linearized KdV. And then that's what you see after evolution. So that's time dependence, right? Now it turns out that this function as a function of x is smoother, is more smooth than at time equals to 0. This kernel has a smoothing properties. So that's known for experts. I don't know. If you study more analytical solutions of exactly soluble systems, then probably it's not your field, but well, Damour, my collaborator, he found some references where it was proven. And what happens if you take the same system, also linearized modified KdV, but follow its spatial evolution? So you should pose 3 functions at Cauchy problem with 3 functions at x equals to 0. Then you develop your function in Fourier integral. And after evolution, that's what you obtain, right? Earlier you had k cubed, and here you have omega to the power 1/3. But the problem is there are 3 cubic roots of omega, and 2 of them are complex. And the complex root, one of them corresponds to instability. And so it grows, the fluctuation grow exponentially. That's the origin of this high frequency noise. Now, what can one do more? So for just ordinary modified KdV with Mathematica, we could follow the evolution only until for the soliton, for exact solution up to this number, and not more. One can make a trick to expand this interval of credibility. And you can do it like that. Instead of field theory system, you can consider mechanical system. Then to this end, you just expand your function in a Fourier series in time, take a finite number of Fourier modes. If you do that, then you discretize the system, and you obtain not a partial differential equation, but you can large system of ordinary differential equations. So that's the simplest. So if you just take 2 modes, then that's what you obtain, just as an example. Also some nonlinear problem, nonlinear mechanical problem, but with a large number of degrees of freedom, which is equivalent to original partial derivative equation. And then you can solve this system. So we did it.
Sorry, what is here? It's what?
It's what? Okay, so there are 2 modes, right? You take this U, I can look at the paper, and you expand it in Fourier series. And suppose you took only 2 harmonics. So psi and chi are 2 harmonics. Okay?
Okay.
Now, it's still the evolution. So you you expand in Fourier series in time, but you still have evolution in X, right? And that's evolution written. So psi and chi are 2 Fourier modes.
So
but you can
there's no dependence on tau on t in this equation.
No, because you took your function, you expanded it in Fourier series, and you kept here only 2 Fourier modes, and these Fourier modes depend on X, right?
Yeah.
Only on X. That's the evolution, the direction of X. But with a computer, you can make many harmonics, well, until it works. And it works for as much as, well, at some point it starts to protest. We had only a laptop. We didn't have large war computers. Then probably this number of harmonics could be more, but we didn't need it. And so that's the number of harmonics, 350. And so we followed the evolution of the harmonics, one of them, and you see that it's quite benign. But then something starts to happen. That's because this high frequency noise, the equivalent of this high frequency noise, also happens here. So you lose control at some X. But here you lose it at X equals 10 rather than X equals 5. Probably very clever, well, numerical people can expand this interval further. How one can do in principle. In principle, you can get rid of this high frequency noise on each step. So it's special procedure, but we are not experts in numerical mathematics. If there are some experts in the audience, then probably they're most welcome to check it. What happens with more sophisticated numerical procedure. And so that's more or less the end of my talk. That's what I want to tell you about. Thank you for your attention.
Thank you for an interesting talk. It's really quite hard to ask something because, I mean, the subject is both familiar and not familiar to me. So I just
Yes,
wonder whether there is anything beyond the observations and conjectures that you can claim about this. Is it true, for instance, if classical system is, well, benign, then something is benign about the
for mechanical
or vice
systems,
versa?
yes. For mechanical systems, it's not conjecture. It's just, well, truth, firm result.
Ah.
For KDV, it's conjecture, yes.
Because KDV is kind of field theory, right? KDV is
KDV is a field theory. That's why it was interesting for me. It's a field theory, yes.
I see. But yeah, because it's all. Is there any? There are lots of the literature about KDV equation is, let's say, outrageously large. So I just wonder whether something like this has ever been observed.
No. I'm surprised, and our collaborator was surprised, who is more expert than me. No. So the only thing, well, for example, I noticed not about KDV, but about tortoise system. That this higher integrals of motion can be treated as Hamiltonians.
Yeah.
Well, also, well, it's not, well, not many people didn't follow that. I found something in this direction, again, in the book of Perelomov, but nothing more. Maybe you know better, I don't know.
But tortoise system is not field system.
It's not field system, it's simpler, yes. But also, well, how to say, for KDV, we just propose to rotate it, right? And for tortoise system, well, we propose to treat higher integrals of motion as Hamiltonian.
And so what? Because there are
well,
various
well, you can do that, and then you just immediately obtain benign quantum benign ghost system, mechanical, not field theory.
Mechanical, I see, mechanical. Because there is field because there's two-dimensional tortoise system as well. People consider it, so probably can give you another example.
Maybe, I don't know that. Probably I don't know. I just don't know that.
Okay, I see. Okay. So that's just kind of experimental data for us to analyze.
Yes,
yeah,
yes,
it's interesting.
Exactly. Yes.
Interesting. Yeah.
But you see, I'm a physicist, and the physics is experimental science.
Sure. That's what I like about physics. I gotta say that I would like to do it myself, but being experimental study is kind of give you some freedom of expressions, let's put it this way.
Yes, I understand quite well that it's not the way mathematicians usually proceed and things like that. Of course, I also would like to be able to prove some exact theorems, exact statements. I know, well, I'm not completely ignorant about the notion of what is theorem.
Sure.
Pythagoras theorem, for example, I know that. But, well, what is possible to do, I tell you, well, exactly, and what is not possible to do, I also tell that it's not yet possible.
Okay. So any other questions or well, remarks or comments?
Can you repeat connection with field theory? I don't understand the idea.
The idea, motivation part.
Motivation.
No. I believe Daniil wants the explanation why PDEs can correspond to field theory, right?
Right.
Partial, of course, well, equations of motion for field theory are partial differential equation. Maxwell equation, well, it's what? It's partial differential equation. If it is your question, maybe you have another question, I don't know.
Yeah, I think it's that simple, Daniil. It's just because when you deal with partial differential equations, it's natural to call it. If you have a partial differential equation which comes from certain Lagrangian system, then it's natural to call it the field system, the field equation.
how we write the function of motion.
Yes, yes. I did it for KDV 1 moment.
Yeah.
So field theory, well, if you have some partial differential equation where the energy is conserved, right? Hamiltonian.
Okay.
Then you can write classical Hamiltonian, and from this classical Hamiltonian you can derive also Lagrangian. For example, KdV can it's just can be treated as a Lagrange equations of the Lagrangian, which I will. Well, here is the Lagrangian.
Okay, and
you just write Lagrange equations of motion, and then you obtain a modified KdV here. Here you obtain modified KdV, but you also can do it for ordinary KdV.
Okay, thanks.
It's not Lorentz invariance. You see, well, people, experts in field theory, including myself, are interested
Lorentz transformation, maybe.
Huh?
Lorentz transformation.
The Lagrangian is not Lorentz invariant. That's what it means.
Okay.
For applications in physics, we're especially interested in Lorentz invariant field theories, right? And this theory is not Lorentz invariant, but still it's field theory.
Yes.
Okay. Thanks.
Okay, we're running out of time in any case. It's I think it's a good time to stop here unless there are some other urgent questions. If there are not, then let us thank the speaker.
Yeah, thank you very much.
Thank you for attention.
I had more or less the same questions as Gosha asked. So
sorry, once more, please. I haven't heard what you
I just said that I had more or less the same questions as Gosha asked. So I'm convinced. Thank you.
You are convinced.
Yeah.
Okay. So you.
Okay. So we will reconvene in a week. Our next speaker is Grigory Papayanov. He will speak about deformation, quantization, deformation theory, and characteristic classes. I'll send the information and abstract of his talk in just by weekend, I think. Yeah. Okay.
Okay. Thank you again. Bye.
Да, я вас тогда включу в список на рассылку. Вы тогда, если хотите, просто приходите, если нет, ну просто как хотите.
Ну, я буду смотреть на название. Если это название хоть что-нибудь мне скажет, тогда я включусь. А если нет, ну тогда...
Конечно.
Спасибо большое вам. До свидания.
Спасибо вам. До свидания.
До свидания.
Александр Борисович, простите, а можно вопрос? Вот я не совсем понял. У нас что с специальным курсом происходит? То есть нам нужно ходить на кафедральный семинар или как нам там его представляют? Просто вот...
Нет, специальный курс – это курс, который сдавать надо.
Это разные вещи.
Семинар – это семинар.
Ну вот семинар... Потому что мне сначала сказали, что вот на семинар Фоменко как бы всем нужно ходить, но потом сказали, что там как бы, ну, для нашего потока отдельные преференции, и типа у нас все отдельно, и вот
нет,
в этом смысле.
Нет, ну, вашим, ну как нет, надо сказать, на самом деле не совсем так. Как раз я вам написал же эти инструкции, странно, что вы спрашиваете. Я очень подробно там все это написал. Что я написал, что спецкурс. Что?
Вы написали по поводу матпрактикума у ВГТ, это немножко другое. Ну, там спрашивают по поводу другого, насколько я понял.
Нет. Я вообще не понимаю, о чем вы говорите. Мне написало 2 человека из вашей группы. Ну, вы же на 3-м курсе, правильно?
Да, конечно.
Ну вот. Вот мне написали 2 человека из вашей группы, я им написал подробное письмо и попросил их всем эту информацию донести. Но, судя по вашим вопросам, Я понимаю, что там творится какой-то хаос. Я очень четко написал следующее, что спецсеминар вашего потока должен быть кафедральным у каждого. За него в конце года ставится зачет. Это спецсеминар. Это то, что вот вы посещаете у нас на кафедре семинар Фоменко. А спецкурсы вы сдаете, точнее не сдаете, потому что у вас программа своя. И у вас в плане никаких кафедральных спецкурсов по выбору кафедры и так далее просто нету. Это было в письме очень четко написано. Я надеюсь, что вы его получили. Вы просто перечитайте. Никакого ВГТ и практикума там не было и в помине.
Меня там... мне никакого письма не приходило. Это приходило ребятам, которые, вот, соответственно, там на другой кафедре, и как бы у них своя проблема была. Так что я вот от вас сейчас
Нет,
слышу.
ну они, вообще-то говоря, должны были всем разослать его. Я же просил их об этом.
Нет, они разослали, но у них так скажем, своя проблема была. Там они спрашивали про то, что у них там какой-то матпрактикум и другое. Я у вас спросил конкретно про этот вопрос. Хорошо, я понял. Спасибо.
Нет. Матпрактикум там у них был отдельный вопрос. Но по матпрактикуму я тоже в этом же письме написал. Матпрактикум — это просто одна из дисциплин, либо есть в учебном плане, либо ее нет. А в этом году у вас ее нету в плане.
Все,
может
хорошо,
быть,
я понял.
Нет, она, возможно, появится в будущем. Просто мне все время переспрашивали об этом, и не очень понимаю, почему. Но, по-моему, там довольно четко, так сказать, я сказал, что если что-то есть в плане, то это есть и в расписании. Если в расписании нет, то значит и в плане нет. Ну, собственно говоря, и все.
Да, а этот семинар, кстати, он в МГУ в итоге появится или нет? Как-то?
Нет, потому что,
Нет, да, к сожалению.
ну, скажем так, можно его насильно, может быть, и можно его внести, но надо понимать следующее, что политика кафедр, ну и нашей в частности, заключается в том, что кафедральный, общекафедральный семинар должны посещать все, и студенты, и сотрудники. Это просто вот такая вот обязанность. Поэтому независимо от того, будет этот семинар наш тоже внесен в базу или нет, отвертеться от кафедрального семинара у вас все равно не получится.
Да, увы. Это такой вот безаловка, которую ничего не сделаешь.
Понятно,
Да.
хорошо, теперь я понял.
А какая за него форма отчетности? То есть ты приходишь, тебя тыкают, типа, что ты есть, все, или там что-то еще надо делать?
За кафедральный семинар вы имеете в виду?
Да.
Более-менее, как
Да,
вы
нет,
сказали.
имейте в виду, Фоменко ведет четкую запись всех, кто посещает. Поэтому те, кто не посещает, зачета не получит просто в конце года. У вас
Понятно.
будет задолженность. Все очень просто. Поэтому его надо посещать. И он то же самое сотрудникам, кстати, пишет. Вот вчера, например, половина сотрудников не было, он сделал выговор всем. Так что он за этим очень четко следит.
Мы с Андреем были, как
Да,
самый
мы как
примерный.
раз мы были, да. Но вот я просто говорю о том, что Анатолий Тимофеевич следит за этим очень четко. Не расслабляйтесь.
Хорошо. Просто студентов там достаточно мало, ну, на семинар.
Но потому что все расслабились. Но вот я говорю вам, он уже вчера всем разослал письмо по кругу. А студенты, если не слишком расслабились, просто не получат зачет в конце.
Письмо счастья. Понятно.
Ну вот.
Ладно, хорошо, я понял. Спасибо. До свидания.
Да, до свидания.
Да, нет. Окей. So, давайте, в самом деле, тогда расходиться.
Да.
Okay. Goodbye, everyone.
Да. Всего
Bye,
доброго.
Jiran, I'll send you an email in a couple of minutes, okay? Jiran, okay? I think he doesn't. Okay.
They are sleeping.
Maybe he's going to join their tunnel.
Yes, maybe.
Okay.
Goodbye.
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 Bye.